Bam! Mr. Tarrou. Okay, flashback. We're going to continue our learning about how to determine whether series converge or diverge. We just in 9.2 talked about determining if a geometric series converges or diverges, and the telescoping series. So when you're given a series and asked if it converges or diverges, the very first thing, and you can do this in your head, is make sure that you look at a sub n, analyze the limit as n goes to infinity, and if that limit is not equal to 0, then you automatically know that that series diverges. If the limit of a sub n, the limit as n approaches infinity of a sub n is equal to 0, you keep going. Otherwise, we wouldn't have to do this whole chapter, most of this chapter 9. So if your series, as you learned in your homework hopefully, if your a sub n expression follows or fits that a times a fixed ratio to a variable power n, that infinite sum is going to be equal to, that series is going to converge to a over 1 minus r when the absolute value of r is greater than 0 and less than 1. That's what we learned in pre-calc for your geometric series. If the absolute value is equal to or greater than 1, then your series is going to diverge. Now, you also have, if you look at a series and you realize that your a sub n term has a denominator that's factorable, then that is more than likely going to be a telescoping series. And we're just going to be looking again at that very most basic setup for partial sums, where the numerator is going to be a constant and the denominator is going to be a factorable quadratic. There's lots of other situations of partial sums that are more complex, but we only need to worry about that one. So you're going to need to be able to factor that denominator and set up, more than likely what you'll have is you're going to have a difference of two terms. You're going to expand that series or that sequence. Actually, what you're expanding is a partial sum, where you have your a sub 1 and your a sub n on different ends, and you're working your way in from a sub 1, a sub 2, a sub 3, a sub n minus 1, a sub n minus 2, and you build up that expansion of the partial sum until you see all of those terms start to cancel out. You get a simplified S sub n formula, partial sum formula, and then evaluate the limit as n approaches infinity of that partial sum. If you get a limit which is a real finite number, then that telescoping series does converge, and it converges to the infinite sum. Remember, your geometric series and your telescoping series are the only two series that you can actually exactly find what that infinite sum is equal to. All the other series that we're talking about from 9.2 to 9.6, when we do these integral, these convergence tests, once you determine if a series does converge, you just have to understand that that infinite sum is going to add up, is going to approach some finite real value. We're not going to be able to find that finite real value, at least at this level of this course, for any other of these types of series that we're given. So what we're learning in 9.3 is the integral test for convergence and the convergence of a p-series. So when you realize that the series given to you is a p-series, that's going to be in the form of 1 over n to a fixed power of p. Those are really easy to determine if they converge or diverge, because you just have to realize that a sub n is in the form of 1 over n. If you have some kind of constant of 2, 3, 4, that's okay as well, and we can actually move that constant out in front of the sigma notation. So when you have 1 over n to a power of p, if that power is greater than 1, then that series is going to converge. P-series converge when p is greater than 1, and p-series diverge if the power on the variable base of n is between 0, greater than 0, and less than or equal to 1. So p-series test is awesome. When you realize that your series given is a p-series, it's really quick to determine if that converges or diverges. We're going to go back to what we learned in pre-calc. I gave you something called a harmonic series. It was just a footnote in pre-calc. A harmonic series is a series where the limit of a sub n goes to 0, but it doesn't go to 0 fast enough for that series to converge. we're going to show how a harmonic series diverges using a integral test, even though it's really technically a type of P series. All the work, really most of the time we spend today is going to be on the integral test because of the work involved in doing this test. If you look at your a sub n term and you realize that it is, if you were to write that a sub n expression as a function and it's something that you can integrate, if you realize that you can, again, you're not going to integrate the a sub n expression or function because the domain of sequences are positive integers. And a condition for you to be able to do integration is the function is continuous. So if you look at a sub n and you're like, hey, if that were a function, I could integrate it, then what you're going to do is, you're going to create a function. Now this says f of n is equal to a sub n. That just means that you're going to create a function for when you plug in that integer domain value, you're going to get the same terms that you would see appear in your sequence, your a sub 1, a sub 2, a sub 3. But ultimately, you're going to be working with an f of x. So you're going to create a function that basically looks exactly like your a sub n expression, only it's going to be in terms of x instead of in terms of n, which is going to open the door to your function being continuous. And you're going to do some condition checks. If f of x, which is a function defined, again, basically the same as a sub n, only the domain's not positive integers. If the function you come up with, f of x, is positive, you cannot alternate between positive and negative. It always has to give for some interval from n, which is a constant, to infinity. F of x has to be positive. It has to be continuous for a specific domain, and it has to be decreasing. Now, to determine if a function is decreasing, if the derivative of f or f prime is negative. So for us to show that f is decreasing, we're going to be having to find a derivative of f of x and over a fixed domain show that that derivative is going to be negative. So if f is always positive for a given domain, if it's continuous, if it's decreasing, then you've met the condition check for doing an integral test. The series from n starts at some constant. Now, when you look at these series notation, you're going to have n equals it's going to have n starting at either 0 or 1. If you need to remove the first few terms and have n start at 6, it doesn't make any difference because this is about a sum where n goes to infinity. So whether n starts, you start really analyzing the infinite behavior of the sum at n equals 1 or n equals 6. N is going from some starting point out to infinity. So if you realize through this work that maybe this function f is only going to be positive starting when n is equal to 3, then that's fine. You would say that the series from n starting at some minimal value going up to infinity, that series along with the improper integral, both of these will either converge or diverge. So you're going to be evaluating an improper integral that we talked about in chapter 8 involving limits. I believe we did that, right? Because we were using we're using AP Classroom instead of the textbook. We're going to be evaluating improper integrals. If the value of that improper integral is a finite number, then that is said to converge, and both the improper integral and the series converge. If the value we get from this improper integral is a positive or negative infinity, that it would be saying that we have a divergent situation, and both the improper integral and the series, they both diverge. That's what we're going to be taking a look at today. So we're going to confirm that the integral test can be applied to this series. Now you'll notice we don't have an a sub n term, so we're going to have to come up with that. Can the integral test be applied, and if so, determine if the series converges or diverges? So we need an a sub n. Now we have, what looks like a partial sum, but after the last plus sign, I'm doing a little dot, 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 indicating, of course, this never ends. What do we need to do to come up with a sub n here? You did a little bit of this in 9.1. And if you don't talk for too long, I'll just edit it out of the video. What did I suggest we do with this in 9.1 to help figure out an a sub n term or expression. You might want to note what n is. So n is equal to 1, 2, 3, 4, 5, and so on. Does there seem to be a break in the pattern of the numerator? Yeah, we're going 1, 2, n is 1, the numerator is 1, n is 2, the numerator is 2, n is 4, the numerator is 4, n is 5, and so on, but there seems to be one that kind of stands out as a little bit out of whack. Which one is that? The third. So how do we get this numerator to match like all the other terms do?
3 over 12.
Okay, multiply numerator and denominator by 3. Is correct. We're going to make that third term. So right now we have a sub n. The numerator is n. Now, the denominator, just for moments of time, because I do want to do a lot of examples today and we don't have a tremendous amount of time. If you can't look at how 1 becomes a 4, 2 becomes a 7, 3 a 12, and so on, then look for some differences. What's the difference between 7 and 4? That's a plus 3. What's the difference between 7 and 12? 5. 12 and 9? 7 and 9 to 28? 9 to 28. 19. Back up. Okay. Obviously knew what I meant because he said 7.
I was like 12 and not 7.
7 minus 4 is 3. 12 minus 7 is 5. 19 minus 12 is 7. That'll have to get edited a little bit. And 28 minus 19 is 9. And why'd you say 7? Did you make a mistake or just knew what I really meant?
I was following a sequence.
His brain completed. It's like one of those papers where all the words are misspelled, but you can still read it. Now we're going to take, so these are called the first differences, and they're not constant. So we're going to take the second differences. Let's take this 3, 5, 7, and 9 and do a subtraction again. How do you get from 3 to 5? Add 2, 5 to 7, add 2, 7 to 9, add 2. So our second differences are constant, which means the denominator is going to be some kind of quadratic or power of 2. So let me get those n's backed up there again. N is equal to 1, 2, 3, 4, 5. What's 1 squared? 1. 2 squared? 4. 3 squared? 9. 4 squared? 16. 5 squared? So our n's squared are what compared to our denominators? Or what do we have to do to n squared to get our denominators? We need to still add 3. So our denominator is going to be n squared plus 3. So the series that we have in this problem, the given series, is the question really is, and for space I'm going to erase this, really the question is, does this series defined by n over n squared plus 3 converge or diverge? So now that we found out what a sub n is, does the series converge or diverge? So we are going to realize that we have a numerator which is a linear function and a denominator which is a quadratic. Doesn't that kind of look like one of our integration rules? When you take a derivative, when you let u be the denominator, when you let u be a second degree polynomial, when you take its derivative, what do you get? If you give me some really embarrassing answer, I'll just edit it out of the video. I'm not doing this to like embarrass you. When you take a derivative of a second degree polynomial, what do you get? A first degree polynomial. So this is probably going to be a u prime over u situation.
Okay, I said u prime.
I can't hear you. I got all this hair in front of my ear. So we are going to let f of x equal x over x squared plus 3. And we are going to make sure that this function stays positive, continuous, and decreasing over some interval where n starts at some constant and goes to infinity. So if f of x is x over x squared plus 3, then f prime of x is what? I don't know. I mean, I don't know the answer either. But how are we taking a derivative? Low. Yeah, I'm doing the rule that we have to. Quotient rule. Low d high minus. What do you want to do?
Oh my god. I was doing integrals, not derivatives.
We're going to in a minute. Yeah, we have to make sure we are going to integrate this function. But first we have to check the conditions. Is f continuous, positive, continuous, and decreasing? We have to make sure f of x is decreasing. The first two are probably going to be rather
So this is just a
obvious.
condition check?
Yes, ma'am. Just the condition check. Let's do that. Let's actually label this. Boop. Condition check. So if f of x is x over x squared plus 3, f prime of x is going to be low d high minus high d low over low low. We might need to, and for AB students, we might need to finish this discussion tomorrow because there is a lot in every one of these sections. So cleaning this up, we have f prime of x is x squared plus 3 minus 2x squared over x squared plus 3 squared, which means that it's negative x squared plus 3 over x squared plus 3 squared. Let me double check that this is right. Okay. So remember, we're taking this derivative, we're finding f prime to determine if f of x, which is, I've basically made it the same as a sub n only with the variable of x, so its domain is sort of like continuous. We're just trying to determine where this derivative is negative. We need f prime to be negative to show that f is decreasing. So the denominator is something squared. Well, anything squared is what? Positive. So all we need to do is figure out when the numerator is negative. So x squared negative x squared plus 3 is less than 0 where? Where is that numerator going to be negative? That's negative x squared is less than negative 3. X squared is greater than 3. When we divide both sides by negative 1, we flip the inequality, of course. And that means that x is got to be greater than the square root of 3. So the square root of 3 is some kind of like 1 point something, right? I don't know. I don't really care what the decimal version is, but the square root of 1 is 1. The square root of 4 is 2. This is the square root of 3. The answer is somewhere between 1 and 2. So this numerator, x negative x squared plus 3, is going to be less than 0 for x greater than or equal to 2. Why am I focusing on x is greater than or equal to 2? Because I'm trying to work on this function is giving the same answer, f of n is equal to a sub n. Yes, I'm looking at a function. Yes, we're about to integrate a function. But ultimately, we're trying to determine the convergence of a sequence. And truly, the domain of a sequence is positive integers. So we really only care about what's happening at the function at that lowest value of n, at that lowest value of x, that x that kind of matches that n. So I'm saying that this f prime, therefore, f prime is less than 0, and f is decreasing. And positive. Is f going to give you a positive answer when x is 2 or greater? The numerator is 2 or bigger, that's positive, and you have a squared term plus a positive number, so f is going to be positive. F is decreasing because the derivative is negative and positive and continuous. Well, it's the only time, where's the only time f of x can possibly be discontinuous?
Square root of 3.
When the denominator is equal to 0. Is this denominator ever going to be equal to 0? No. So this function has a domain of all real numbers. So f is less than 0, therefore f is decreasing, positive, and continuous for x greater than or equal to 2. So we've met the condition check. Now we have to do the improper integral. This is all just the condition check. So now, let me pick a different color just to show. We're going to actually do the integral. We're going to be evaluating the improper integral, where the definite integral starts at not 1 but 2, because f prime is not negative until x is greater than or equal to 2. So we're doing a definite integral from 2 to infinity of x over x squared plus 3 dx. Now, if you want to make your notation really, really perfect, a condition check for definite integrals is that the function's continuous over a closed interval, and this is an open interval. So like we did with improper integrals, we're going to do the limit as b approaches infinity of the definite integral from 2 to b of x over x squared plus 3 dx. Now, if u I'll do this in blue. We're going to let u equal x squared plus 3. If we let u equal x squared plus 3, what's du? 2x dx. So if our denominator is u and we want our numerator to be u prime, we need a 2x, not an x. So what am I going to do? I'm going to introduce a multiple of 2 and balance that with a division of 2 and integrate. What is the integral of u prime over u? Natural log of the absolute value of u. Thank you. So we have 1/2 times the natural log of the absolute value of x squared plus 3 with an upper limit of b, lower limit of 2. And we haven't done anything to get rid of that limit notation yet. So we also have the limit. We have 1/2 times the limit as b approaches infinity. I haven't made a mistake, have I? You guys are supposed to help me when I make a mistake.
Yeah.
Why are there 2 1/2s? What I meant to do here.
I was wondering, I added that. So I was like,
Okay, we want this is correct. And then I'm going to take the 1/2 and move it out.
wait.
Whenever you have a constant coefficient, it's just going to be easier if you move it out in front of your arithmetic work. In this case, your limit work. So we have 1/2 times the limit as b approaches infinity of the natural log of b squared plus 3, absolute value, yeah, I said that, minus the natural log of the absolute value of 2 squared, which is 4, but I want to write 2 squared, plus 3. So we have 1/2. As we let b approach infinity, what's the natural log of infinity? The natural log function is not asymptotic. It never stops going up. So what's the natural log of infinity? It's another infinity. And minus the natural log of 7, but who really cares? Because we have infinity as our answer. Is that a real solution, or is that, it's not a real solution, right? That means that our improper integral is diverging. So therefore, by the integral test, the given series diverges. Bam! Would you like some review? Huh? You want some review of some Calc BC stuff? let's take a look at example 2. Okay, so we have the series where n starts at 2 and goes to infinity of the natural log of n over n to the 4th power.
Oh, but we already have
Does that look like something, what's that?
nothing. We're already given A then, so that makes it like easier.
Mm-hmm. Okay. So does this series converge or diverge? We don't need to do like a whole L'Hopital's test. Okay. Do you believe this? The limit as a sub n approaches the limit as n approaches infinity of a sub n. What's your natural log function look like? It's asymptotic to the the y-axis, and then it kind of levels off. It almost looks like there's a horizontal asymptote, but there's not. The natural log function grows very slowly. What's n to the 4th look like? That's if n is going to start at 2 and go to infinity, you're talking about bases that are larger than 1 being raised to the 4th power. 2 to the 4th, 3 to the 4th, 4 to the 4th, 100 to the 4th, million to the 4th. This is basically exponential growth. So what's growing faster, the numerator or denominator? The denominator. So the limit as n approaches infinity of a sub n is going to be 0. It's not going to be something else. So there's the door open for this possibly to converge. Is this something that we can take? Well, actually, first of all, does it look like a geometric where you have a fixed base, a fixed ratio, and variable exponent? No, not even close. Do you have a denominator which you can factor? Definitely not. Not where you have like
Oh, yeah.
a pair of linear functions that are factors. It's not, and we're not going to get to it today anyway, but it's not a 1 over variable-based fixed power. We do have a variable-based fixed power, but the numerator is not 1 or a constant that we can just move out in front of sigma. So the only test available to us to determine whether the series converges is the integral test. So we need to let equal the natural log of x over x to the 4th. Now, natural log can be negative, but the natural log function is positive after it passes through the coordinate of 1, 0. So this numerator is always going to be positive. Anything to the 4th power, actually it doesn't even matter if the power is even or odd because our domain of series are positive integers. So when you put any number, any positive number to a power is going to be another positive number. So f of x is going to be positive. It also has a domain of x is greater than 0. So it's going to be continuous. So the only question is f of x decreasing? How do we find f prime? Low, d high, minus
Oh my god.
high, d low, all over low, low, edit, cut, redo. Now we've got x to the 3rd minus natural log of x times 4x cubed over x to the 8th, which means that f prime of x is 1 minus the natural log of x over times 4, 1 minus 4, over x to the 5th. So when we consider that the domain of series is positive integers, which means the domain of our function is going to be some kind of positive x, a positive number to a 5th power is always going to be positive. So we need to determine where the numerator is not going to be positive, but we want this derivative to be negative. We need to find out where 1 minus 4 natural log of x is less than 0. So to continue this, we need to work on, go back to blue here. We need to do 1 minus 4 natural log of x is less than 0, which means 1 is less than 4 natural log of x, which means that 1/4 is less than the natural log of x. We're trying to find out x. We're trying to find out where this expression is less than 0, thus making the derivative negative. So we're going to make both sides an exponent of e, and we have x has to be greater than basically the fourth root of e. E is somewhere between 1 and 16, right? So this is an answer somewhere between 1 and 2. So x is some decimal between 1 and 2. So x needs to be greater than or equal to 2, which is probably why the textbook gave us a series where n started at 2 and not equal to 1. Not the textbook, my example. This isn't a textbook problem. So now we know from all of this, this is all a condition check again. Should have highlighted that. F is positive, continuous, and decreasing for x is greater than or equal to 2. So our condition check is done. We can apply the integral test. And I know this is going to take some work, so I'm going to erase our condition check. Okay, so our conditions are done. We are going to be doing an improper integral where the limit as b approaches infinity of the definite integral where it starts at 2 and goes to b of the natural log of n over, not n, x's, the natural log of x over x to the fourth. That's a small nuance, but it's important, right? You need that continuity. The domain cannot be positive integers. What's that? D of x, thank you. So think about all those integration rules that we have. This fits none of them. So we're going to bring the division of x to the fourth up, and we have the limit as b approaches infinity of the definite integral of 2 to b of x to the negative fourth natural log of x dx. And there is, in Calc 1, I say a bunch of times there's no product rule for integration. But we're not in Calc 1. We're in Calc 2, and what does that look like? Integration by parts. That was a long time ago, before winter break. That's why I picked this question to do. So your integration by parts is the integral of uv, u dv, is equal to u v minus the integral of v du. And you want to look at this integrand and pick a u using your brains or the LIATE acronym. Logarithms, inverse trig functions, algebraic expressions, trig functions, exponential functions. You're looking for the factor that is easily derived, or you can easily take a derivative of, and it gives you a simpler solution. So what's the derivative of natural log of x? 1 over x. So if you take the derivative of natural log of x, you get an algebraic expression or function as opposed to a logarithmic function. That is a simpler function. So you're going to let u equal the natural log of x du is going to equal 1 over x, which means dv is going to be x to the negative 4 dx, and v is going to be the integral of that, which means v, raise the power up. You raise me up, and then you divide. So we have v is equal to negative 1/3 x to the negative third power, or negative 1 over 3 x cubed. So now we have, I know you want to take this next year. So now we have u, v. So we have negative natural log of x over 3x cubed minus the integral of v du dx. So we have negative natural log of x over 3x cubed. Negative and negative is positive. So plus, I'm going to bring the 1/3 out. So plus 1/3 times the indefinite integral. X cubed times x is x to the 4th, but it's in the denominator. So it's going to be, we're going to be integrating x to the negative 4 dx. Now, what's the integral of x to the negative 4th?
Negative 1/3 x.
Yeah. So we're going to have negative natural log of x over 3x cubed plus 1/3 times, bring this power up, like you said, thank you, x to the negative 3rd, divide by negative 3. I'm doing an indefinite integral, so technically right now I need the plus c, even though we're not going to use that. Negative natural log of x over 3x cubed minus 1/9, or minus 1 over 9x cubed plus c. Okay. Or negative 3 natural log of x minus 1 over 9x cubed plus c. Now, I don't like doing integration by parts with definite integrals. So you might have noticed that I just stopped and did a whole bunch of scratch work with an improper, an indefinite integral. So this is the answer. So now that we're going to come back over here and say that we have the limit as b approaches infinity of negative 3 natural log of x minus 1 over 9x cubed with your limits of b and 2. All right, so our last step here is to evaluate this limit. We got the limit as b approaches infinity of negative 3 times the natural log of b minus 1 over 9 times b cubed minus negative 3 natural log of, now we're plugging in our lower limit of 2, natural log of 2 minus 1 over 9 times 2 cubed. Now, if this were a simpler problem, we'd actually have to do L'Hopital's rule to prove that the limit as b approaches infinity of negative 3 times natural log of b minus 1 over 9b cubed is going to be equal to 0. But this is part of a really much more complex problem. So we've got that natural log function growing really, really slow as b approaches infinity. And in the denominator, as b is getting larger and larger and larger, you have that exponential function to a power of 3. That 9b cubed, that denominator is going to grow a lot faster than the numerator. And that first term is going to come out to be 0. So we're almost done. This limit is going to come out to be 3, as we distribute the negative sign through here. 3 natural log of 2 plus 1 over basically 9 times 8. Well, this is a real finite limit. Therefore, we have shown that this improper integral does converge to a real limit, thus the given series by the integral test. You do need to name the test at the end of your conclusion that you use to come to this conclusion. By the integral test, the given series converges.